So we are filling out the seating chart right now. Everybody, every day, we're filling out the seating chart. So please make sure you have put your name on the seating chart. Remember, we're trying to sit in the same places every day, so we're close to the same people. We've got about 2 more minutes. How y'all doing with the homework system? Okay. It can be a challenge in the beginning. It really can be just learning.
I feel like the practice one made it seem so much harder than I was going to.
Well, the practice one goes through a bunch of different things that we're going to do the whole semester, whereas like the first homework is just a small portion of it. So by the time you get to really building molecules inside the homework, you'll be really comfortable with it already. So yeah, so the first one is kind of a challenge. It really is. All right, so don't forget to put your name on the seating chart. Even if you come in late, when you come in, even if it's not up on the screen, it's still available to you. I don't lock it until after class. So just make sure you put it in at some point before you leave the class. All right, so I will go ahead and start, and I'll start with a joke. And I want y'all, I'm gonna preface this joke. I want you to picture a 9-year-old telling this joke and not me, okay? So you have to picture like a little 9-year-old boy telling this joke. All right, knock, knock. T-Rex. What? There's a T-Rex at your door and you want to know his name? It's currently my child's favorite joke. I cannot tell you guys how many times I've heard that joke. And I must respond every time. Even though I know it's coming, but that's okay. All right, I'm going to say one more thing before we start on actual chemistry. So I'm going to ask everybody, the whole class period, so I never have to stop class again, to make sure that your mask is covering both your nose and your mouth. I don't want to have to stop class and say that one more time. Y'all, most of y'all are in here nursing. Okay, if you're nursing, you guys are going to become the pillars of the medical community. So you really need to set an example for everybody else. So this is not the class that I should have to remind that why we're wearing the mask, why it's important, and why we needed to cover both our nose and our mouth, okay? So please, please, please do me that favor and keep it on the whole class, okay? It's really for everyone's safety. All right, so chemistry, back to chemistry. Oh, and what do we have coming up next Thursday? Exam 1. Exam 1. I know it's quick, but exam 1 only covers chapters 1 and 2, which is kind of nice. It's not a ton of material. It's only chapters 1 and 2. So now's the time. If you have a question, you need help, don't come and ask me Wednesday night. Don't send me a bunch of emails Wednesday night. I don't know how to do this. Don't do that. Come and ask me early, okay? Go to tutoring early. Read the book, watch the lectures, right? Do not get behind, okay? All right, let's see. Minimize this stuff. The wrong things up. Okay, so you need your eye clicker out. You need your best friend out. And you'll probably need a calculator. So I shouldn't have to say that from here on out. When you sit down, you should be eye clicker ready, calculator ready, best friend ready, and whatever else, notes, whatever you want to have open during eye clicker questions. Okay, so here we go. You full screen. All right, so you have 1 minute. How many electrons are present in a neutral atom of potassium? How many are present in a neutral atom of potassium? Notice I say neutral. One minute. Okay. Closed it at 1 minute. Make sure you've clicked in. See if you people still clicking in. Please click in. Okay, so what are we at? 52? I'll close it at 1:10. All right. So now you get to turn, you get to talk to your partners, talk to the people around you. I'll give you 30 seconds on this one. 30 seconds. Remember to click in again. Hey, we got about 5 seconds left. So we had 50 something clicked in earlier. So make sure you clicked in. Come on, y'all. What was it before? 50, 54? Come on, y'all. I'm closing it at 50 seconds. I'm closing it. So 5 seconds. 2, 1. Okay. So how many electrons are present in a neutral atom of potassium? So we go and we look at potassium. What letter is potassium? K. K. So there are 2 numbers inside the box on the classroom wall, 19 and 39.10. Which one is it? It's the 19. It's absolutely the 19. Let's see how we did on round 1. Oh yeah, see, look, we increase. I like this. I like this method. It's good. So what is that 39? 39.10, right? It has a K and it has a 19. So what's the 30, right? 39.10? That's the box. What are these two things? So do you notice how 19 is a whole number? And you look on all the periodic tables, do you see those blue numbers at the top? They're all whole numbers, right? So you must be counting something. What are you counting? Protons, number of protons. And we know in a neutral atom, what? Number of protons is equal to number of electrons. Okay, so that's a neutral atom. So what is this down here? It's not a whole number. So it's not like we're counting protons. What are we doing? This is the average atomic mass. So if you took the average mass of an atom of that element, that is what the mass would be. And we're going to talk a lot today about what that really means. Okay. All right. So what is atomic number? What is the atomic number? 1 minute. Okay, you have about 10 seconds left. Make sure you click in. Okay, so turn, look around, talk. Give you another minute. 1 minute. Okay, you have about 10 seconds left. All right. So what did we say? What is the atomic number? Ooh, very good. Okay, so B is equal to the number of protons in each atom of the element. So when we drew that thing just a second ago, when we drew this, which one is the atomic number? The top one, 19. This is the atomic number, right? We just now named it. Okay. All right, so I think I have to grade. Wait, let me go back to grade it again. Okay, look, we did it. That was a great increase. That was awesome. That was awesome. Okay, let's do one more. One more. All right, tell me about protons. Which statement is correct about protons? Remember, this one's by yourself. This one's by yourself. All right, 10 seconds. Okay, so now you can turn and talk to the people around you, and we'll go again for a minute. I don't think we really need a minute on this one, actually. 30 seconds would probably be good. We'll see if we can get up to how many we have, 50, 55? We can get up to that number. I think 30 seconds is going to be plenty. So don't forget to click back in once you decide. Okay, we only got 50. Looking for like 55. So click in if you have not clicked in. Guess we'll wait the whole minute. Okay, 10 seconds. Sometimes knowing the timing on these is a challenge. All right. So what did we say? Protons have, oh, very good. Protons have a mass of about 1 AMU and a charge of +1. So what did we say before? Oh, very good. Okay. So we knew. What has a mass of about 1 AMU and no charge? Anything? A what? A neutron has a negligible mass and a -1 charge. Electron, a negligible mass and no charge. Nothing, it doesn't exist. Okay, a mass of about 1 AMU and a -1 charge. No, nothing. And then D was the proton, right? That's right. Proton, neutron, electron. Yes, ma'am. We're going to find out today. We're going to find out today. That's an awesome question. I'm going to show you that today. Okay. I'm not going to say the changes. Okay. So this is kind of where we left off, right? View full screen. Okay. We did fluorine containing 10 neutrons. We did that, right? Yes? But I assume so, unless somebody tells me otherwise. We did 2.10. We're on what? 2.12. Oh, you did that one. Okay, okay. You did that one. Sometimes it's hard for me to remember if it was my 5T or my 4T, what we did. Okay, so we are now writing symbolic notations. And when we do symbolic notations, we really need to give 3 different pieces of information. What 3 pieces of information are we giving? Symbolic notation. What is symbolic notation? We're going to give the element symbol, right? Where do we get this element symbol? Periodic table. Periodic table. So this is the element symbol. Okay. We just put it as X. There is no X element, but you know. Then there's a number at the top and there's a number at the bottom, right? What's the number at the top? Give me the scientific name for it. Atomic. Why do we call it the atomic number? Because it's the number of what? Of protons. What determines what kind of an element that atom is? How do I know it's a carbon versus a potassium versus lithium versus hydrogen? What's the defining characteristic? Number of protons. So that's why we call it atomic number, right? Because we're going to identify what that atom is based on that number. Okay, what's the bottom one? What is it? Okay, there's mass number and there's atomic mass. Which one? Are you ever going to see a decimal here? No, we never see a decimal. So it must be a counting number. So it must be the mass number. It's the mass number. What is the mass number?
Protons.
Protons plus neutrons. Why do we only count protons and neutrons? Why don't we count electrons?
Because they don't weigh, they swirl.
Yeah, they don't weigh very much, right? They weigh 1/2000th of a proton or a neutron, but a proton and a neutron, they have about the same mass of 1 AMU. So that's why we count them.
That's not the same thing as the atomic number.
No, it is not. No, it is not. We're gonna tackle that today. All right, so if I have an atom, let's do A. If I have an atom that has 3 protons and 4 neutrons, how would I write its symbol? Let's do the numbers first, and then we'll get the element name. 3 protons, 4 neutrons. What number goes at the top? 3. What number goes at the bottom? 7. How did you get that? All I did was add 3 to 4, add my number of protons to my number of neutrons. Now, how do I know what symbol to put there? Do I look at the 3 or do I look at the 7? I look at the 3 because that's the number of protons, that's the atomic number. So I go to my periodic table, what has 3 protons? Lithium. Okay. B, we have 7 protons, 10 neutrons. Now I'm going to ask you, give me the element symbol first. What is the element symbol? 7, I look, and that is nitrogen. So where does that 7 go, top or bottom? What goes at the bottom? And how did you get that? You added 7 plus 10, right? Okay, C, let me extend the page. I'm gonna get cut off. Okay, we have 15 protons and 16 neutrons. What is my element symbol? What is my element symbol? So go look at 15. What element has 15? We abbreviate with a P. So what number goes on top? What? I did that wrong. I told y'all that wrong. I did that wrong. It's the big number. I'm sorry. Y'all. Oh my gosh, it's a long day. Okay. I had it, y'all. I got freaked out. I got totally freaked out today. There's a snake in my backyard, a very big snake. And if you would know me, I do not do well with snakes. I'm sorry, y'all. Atomic numbers at the bottom, mass numbers at the top. I was like, that just looks so wrong. So switch them. The big number is always on top. So just switch them. So 7 and 3, 17 and 7. And then tell me about phosphorus. What goes on top? 15 plus 16, 31. What goes on bottom? 15. And the way you can remember this when you're not like totally freaked out because there was a snake in your backyard is when you do this, you should be able to subtract these two. And what do you get? Number of neutrons. So how many neutrons? 16 neutrons, right? You should always be able to subtract them and get the number of neutrons. So it's like the math problem's already set up for you. You just have to do the subtraction. Woo. Do not like snakes. Okay. But that is not part of the symbol, so don't write that. But okay, let's do it right from here on out. All right, D, what do we have in D? 46 protons and 60 neutrons. Ooh, we're getting big. So 46 protons is what element? Pb. Palladium. What goes on top? 106, the big number. 106 goes on top. What goes on bottom? 46. 46. Okay, Good. Big number on top. Number on top. Put to that note. Big number, which is the mass number, our number of protons plus our number of neutrons. Okay, cool. All right. Determine the number of protons, neutrons, and electrons for each of the following atoms. Notice which number's on top, the bigger number or the smaller number for all of these. Always the bigger one. So all you have to do is set up a subtraction problem. So we're going to do protons, neutrons, and electrons. Okay, and how do we know that these are neutral? Because they're atoms. What would we call them if they weren't neutral? We would call them ions. But because they're neutral, what does that tell me about protons and electrons? They have to be equal. You have to have an equal number of positive things as you do negative things if you're going to be neutral. So the first one, hydrogen. How many protons? 1, that's the bottom number. Okay. Fill in your electrons right away. Go and do that. Now tell me about neutrons. 1, how did you know that? Because all I did was 2 minus 1 is 1, right? Because if you do this, 2, 1, you do a subtraction, you get 1, and that's your number of neutrons. So it's like the problem's already set up for you. Okay, C and D. All right, so what do we get for B? Aluminum, how many protons? 13. How many electrons? 13. Now, how many neutrons? 14. 14. Y'all see where I'm doing the math? Okay. All right, sodium. How many protons? How many electrons? Okay, now subtract 23 minus 11. How many neutrons? 12. Okay. Bromine. How many protons? 35. How many electrons? 35. Now subtract 79 minus 35. How many neutrons? Okay. Not too bad, right? So the only thing is when you're putting this into the homework, because you'll get some homeworks, right? So say you were trying to do this hydrogen one. If you type the name in, then you have to introduce a superscript and a stacked subscript. So the two have to be one on top of the other. If you had it to where you were trying to write it, whoa, and you do first the superscript, then you do the subscript, you see how they're off center? They're going to mark it wrong. So it has to be a stacked subscript. So be careful about that. Okay? Yeah? All right. Okay. So remember when we talk about isotopes, what's the definition of an isotope? What about carbon? How many electrons, I don't know how many electrons, how many protons does any carbon atom have? If I look up there, I have 6 protons. So anything that has 6 protons must be called carbon. I could gain or lose electrons, and what would happen? I would have ions, so I would be charged. That's okay, that can happen. What happens if I add or lose neutrons? Is my charge going to change? No, because they're neutral, but what's going to change? The mass. The mass is going to change, right? So I can have carbon 12. I could have carbon 13. I could have carbon 14, right? How many protons does each of these atoms have? I have 6 protons, 6 protons, 6 protons. How many neutrons? They're all here. How many neutrons? 12 minus 6 is 13 minus 6 is 14 minus 6 is 8. So when we report what is an isotope, I would say it's the carbon-14 isotope because I know that the number of protons isn't changing. It's the number of neutrons that's changing, right? Now, look up at your periodic table. Look at carbon. Carbon's atomic mass is 12.01. Does that mean that every single carbon atom weighs 12.01 AMU? Why not? Could they? Based on what we wrote? They can't. A carbon-14 atom is going to be heavier than a carbon-12 atom. So how can we get an average mass of 12.01? Why isn't it 12 plus 13 plus 14 divided by 3? Right? It's a weighted average. So somebody do that. What's the average of 12 plus 13 plus 14? What do you get? 13, right? 13. So why is it not 13 on there? Because it's what's called a weighted average. That's what's on the periodic table, is a weighted average. So if you look up there on the periodic table, it's 12.01. What does that tell me about the different carbon isotopes? Which one do you think we have more of? Carbon 12. Most of the carbon on Earth is carbon 12. You got about 1% carbon 13 and a tiny amount of carbon 14. But 99% of all carbon on the planet is carbon 12. So the mass is just slightly greater than 12. So that's why it's an average weight. You have to take into account the percent of each isoform, of each isotope that is present. Okay, so that's why you're always going to see those decimal points in those weights. Okay, we'll get all that in a video. All right, so the mass of an isotope of carbon-12 is exactly 12 AMU. The atomic mass for carbon, as seen on the periodic table, is 12.01. Explain the difference. Oh, we just did this. Okay, so explain the difference. What do we say? The atomic mass on the periodic table is what? I'm going to say PT, that's periodic table, is what? A weighted average of all isotopes, isotopes, isotopes of carbon. So what does that look like? You're never going to actually have to calculate this for me, but if you were going to do a mathematical equation, and you don't have to write this down, I just want you to understand it. How would I do that? How do I do a calculation that's a weighted average versus a regular old average, right? I had 12 plus 13 plus 14 divided by 3. That's an average formula, right? What do I do if it's not average? What if it's weighted average? What do I do differently? I do 12 times the decimal form of the percent. So if I tell you 99% of all carbon on the planet is carbon 12, I'm going to multiply it times 0.99. Then I'm going to do carbon 13, and I told you that's what? 1%. So that's 0.001, right? Plus what? 14, and then it's like a tiny, tiny, tiny. I'm just going to put tiny, right? Tiny, and divide by 3. So that's all you do. That's the only difference. But you're never going to have to do this. You're never going to have to do this. Okay? Cool? Yeah? All right. How are atomic mass and mass number similar? How are they different? Okay, what was atomic mass? This is our weighted average, right? And what is mass number? Remember, it's a number, so it's a counting. What are we counting? Things that have mass. So this is a count of protons and neutrons, right? Yes? Okay, so how are they similar? What are they both primarily dependent upon? What's that? They're dependent upon number of protons and neutrons, right? Because if you have more protons, what's going to happen to your atomic mass? It's going to go up. What happens if you have more protons? What happens to your mass number? It's going to go up, right? They're both going to go up. But how are they different? We know that mass number is simply a count, right? It's simply a count. You're counting. So your mass number is going to be different for every what? For every, I'm getting too close to the bottom. Different for every isotope, right? But the atomic mass is the same because it's already taking into account all the different isotopes of that one element, right? Y'all with me? Feels like a Monday today, huh? All right, so how are they different? They're different. The mass number is different for every isotope. And my weighted average takes into account what? We call it the percent abundance, right? That's an easy way to say it, percent abundance. How abundant is this one isotope in nature? Something that's 99% abundant is mostly that, right? So it's exactly right. So see how they're different, how they're similar? Even though they sound very similar, they're not. Okay, we have 3 naturally occurring isotopes, and this time we're going to do magnesium. We have magnesium 24, magnesium 25, and magnesium 26. Tell me something about magnesium before we do this. Mg, what must every single atom of magnesium have? Every one has 12 protons. Other things can vary, but that will never vary. How many neutrons are present in each isotope? So in magnesium 24, what is this 24 telling me? This 24. This is the mass number. Remember when we did it in the symbol notation, we put it at the top? So B says write the complete symbolic notation for each isotope. So let's do that. Mg, what's the 24? Where does the 24 go? At the top. What goes at the bottom? 12. Oh, look, we have a perfect math problem already set up for us. 24 minus 12 is 12. So how many neutrons are present in magnesium 24? So this is 12 neutrons. Okay, how about magnesium 25? I'm going to put 25 and 12. So now I have one more, right? Because what happened to my mass number? I went from 24 to 25. Did my number of protons change? No, it had to be my number of neutrons. So magnesium 25 has 13 neutrons. And then let's just do magnesium 26. 12 on the bottom, because it has to be, right? So how many? 14 neutrons, right? Okay, so based on the average atomic mass given on the periodic table, which is what? (24.30). Which isotope of magnesium is the most abundant? Magnesium 24, because the average is 24, because the average atomic mass is closest to that mass number, right? So you don't have to do the calculation, but you have to be able to look at the isotopes and tell me which isotope is most prevalent. You absolutely have to be able to do that. Okay, some of the naturally occurring isotopes of 10 are 10, 118, 10, 119, 10, 120, and 10, 124. How many neutrons are present? And write the complete symbolic notation. Let's do symbolic notation first, and then we'll go back and catch neutrons. So for 10, 118, what is 10? What's the symbol? SN is 10. Isn't that weird? SN. So SN, what goes on the top? 118, what goes on the bottom? 50. Okay, so that's 10, 118. How about 10, 119? It's just 119 on the top. What goes on the bottom? Y'all awake? What goes on the bottom? 50. All right. Oh, y'all are awake. All right, 10, 120. What goes on the top? 120. What goes on the bottom? Yay. All right, 10, 124. What goes on the top? What goes on the bottom? Okay, how many neutrons are present in each isotope? I'm just going to kind of write it down this way. How many are present in 10, 118? Do 118 minus 50. 68. How about 119? We only went up by 1, so it's just going to be 1 more, 69. 120, 70, 124, be careful, 74, because we went up by 4 instead of by 1. Good? Y'all got this. Y'all got this. This is easy. Got it. Okay. Now that we know what's inside the nucleus, now we're going to talk about some really cool, kind of scary stuff, radioactivity and how that works inside the cell. So you need to know these. Look on your Oh Best Friend. Is this on your Oh Best Friend? This is not on your Oh Best Friend. Okay, so what should you do? Like, please, please, please learn this. All right, we have different kinds of radiation that is produced inside of atoms. The first one is called an alpha particle. And an alpha particle, what actually ends up happening is that you have a charge of +2. So these are particles that are being emitted. And this image comes straight from your textbook. So you have this in your textbook. So that alpha particle has a charge of +2. So what do you think might compose that alpha particle? If it's a +2. 2 protons. Okay, now look at the symbol. Either you can make it a little alpha, or you can write He 4/2. What is that telling me? 4/2. Not only do I have 2 protons, that's the bottom numbers telling me I have 2 protons. What else do I have? Not 2 electrons, because electrons don't have mass. Look at the mass number. Remember we said you could set it up as an equation, 4 minus 2, what do you get? And then 2 what? 2 neutrons. So what is an alpha particle really? 2 protons and 2 neutrons, right? How else are you going to get a mass number of 4 and a charge of +2? I suggest for an alpha particle, you write the helium symbol, because otherwise you're going to kind of forget what it is and what it means. So I suggest the helium. A beta particle is another type of radiation. And in this type of radiation, what you actually have is you have a neutron inside the nucleus of the cell, and it actually ejects a part of itself, and that ejection actually becomes an electron. And when that neutron ejects that electron, the neutron then becomes a proton. It's kind of crazy. But if you are emitting out an electron, what's the charge on an electron? You're emitting an electron. An electron is -1, negative, right? So the charge on the particle that's leaving the nucleus is a -1. So we represent that in 2 ways, either beta, or you put a little letter E for electron. And I have to subtract 1. Why do I have to subtract 1? You're losing, you have particles inside the nucleus that are changing, right? And so that's why we have that -1 there, because we're losing that proton, okay? But we don't have a mass. Over here, you'll see a mass of 0, right? Because an electron is 1/2000 of the mass of a proton or a neutron. So we don't really say it has mass. Okay, the next one is a gamma. So gamma radiation is just waves. It's not a particle. And so it has no mass and it has no charge, but it's very, very dangerous. So you have to be careful about that one. A positron. A positron is kind of the opposite of a beta particle, right? Look at the symbol. Compare the symbol of the two. What's different? It's what? Well, the beta particle is negative. The positron is positive. Positron's positive, right? It doesn't show one, but if there's nothing there, it has to be positive, right? So I'm actually releasing a positively charged particle. So I'm releasing a proton. So if I'm changing my protons inside of my nucleus, what's going to happen to my element? Am I going to have the same element anymore if I change the number of protons? No. So in radioactivity, a lot of times what happens is you change from one element to another element in that reaction. It's really cool. It's really, really cool. All right, the last one is a neutron. Now, a neutron is kind of special because we don't normally release neutrons. Usually we bombard an atom with neutrons and we make isotopes. So here we usually like you shoot neutrons at an atom to make an isotope. So you got to think about in medicine, right? Do we use radiation, radioactivity to treat our patients? Yes, in what? A lot in cancer, right? So how do you make something radioactive? I want to give a patient something that's radioactive. What makes something radioactive? Having a really strange ratio of protons to neutrons. So I can actually take an atom and I can add neutrons to it and make the nucleus unstable and now have a radioactive substance that I can then use to treat a patient with. It's really cool. Really cool. Okay.
So,
yes.
okay, so for the beta, what's being released there?
A high energy electron.
Okay.
So see, you look at the charge and you know what's being released, right? Here, what's being released has a charge of +2. So we know there are 2 protons there, but we look here at the 4 and we say, oh, that's 2 protons and 2 neutrons. Here, we're only losing an electron, but we're losing an electron because we've converted the proton into a neutron and an electron. So we release the electron, right? Okay, and that's why your mass number doesn't change, because you just converted proton to neutron. They have the same mass.
That's what I was.
And then here, gamma is, you're not really changing number of particles of anything. Then positron here, right? You're taking one of your protons. You're gonna release a proton because your charge is +1, right? Okay. All right. So if you understand the table, right? What you really need to know is the symbol. If you know the symbol, you can figure out everything else. So my suggestion is, if you know the name and you know the symbol, you're going to be fine. Okay. So what's the charge on a beta particle? Look at just the symbol of a beta particle. I've written all over this table. What's the symbol on a beta particle? We have 1/-1E, right? So what's the charge? Is there something charged in that symbol? Yes, right? So it's a -1 because it's an electron that's being emitted. Okay, an alpha particle. Look at the alpha particle. If there's no negative sign there, what do you automatically know it is? Positive. That's a +2 down there. So what's the charge on a beta particle? +2. What's the charge on a positron? If there's no negative there, what is it? Positive. So what's the charge? +1. Well, look, we just filled in that column, right? Okay. All right, let's see. Oh, I did 23 and 24 on the thing. That looks like this handwriting though. Looks like I didn't erase from last time. Okay. What form of ionizing radiation is most similar to X-rays? You know, you go to the dentist and you get an X-ray, right? So an X-ray does not come from the nucleus, right? It's an electron. So it's a non-nuclear reaction. And it's X-rays. When you think of rays, what do you kind of think of? Like the sun, I think of like waves of light coming off of the sun, right? This brilliant sun that, you know, I'm a horrible artist, right? But I have these waves coming off of the sun. And so that's what I kind of think about with X-rays is my waves. And the same sort of thing, there's another one that is emitted from the nucleus that's similar. That's just waves. It's not a particle. Which one is not a particle? Gamma. Gamma radiation is most similar to X-ray radiation. Why? Because they're not particles. So these are neither one, they are not particles. But how often do you go and get an X-ray? Relatively frequently, you know, like you go to the dentist, you get an X-ray every year, you break your foot, you get an X-ray, right? It's not a big deal to get a couple of X-rays, but we really don't want you getting gamma radiation unless you need it. So X-ray is much lower energy. Lower energy. You have to be very careful about gamma radiation. Okay, so how much radiation do we get normally? We just talked about like X-rays, right? But if you step outside, you're getting radiation from the sun. You're getting some all the time, right? How do you know that? What happens if you go outside and you don't put sunscreen on and it's really a bright, beautiful day? You get sunburned. Why do you get sunburned? Because you have been exposed to radiation. That radiation has damaged the DNA of your cells. Your cells see that DNA damage and say, Oh my gosh, I do not need to replicate, because if I replicate, I'm going to make cancer. So they put little markers on the outside of the cells that say, come and eat me because my DNA is wrong, my DNA is damaged, and your immune system goes in and kills those cells. And that's why you turn red, because you got a sunburn. It's true. If you're like me, it takes about 10 minutes out in the sun. So if high doses of radiation are harmful, right? It's harmful. We know that. You go stand in the sun and you're going to get sunburned. What's the rationale behind radiation therapy for people with cancer? I have people who are already sick. So their cancer cells are not healthy. That's very true. Their cancer cells have mutations inside of the DNA, right? And normally what catches those mistakes? The immune system. The immune system recognizes cancerous cells and kills them all the time. Trust me, your immune system has already done it. But after years and years and years of exposure to the environment, you're going to get mutations and your immune system is going to miss some of those cells that are messed up. And that's how we get cancer. And a lot of times it takes an accumulation of a couple of mutations, usually like 5 to 8 in key genes, to make cancer happen. So yes, we have these cells that are unhealthy, that are not replicating properly. So why do we give people more radiation? What's a key characteristic of a cancer cell? Do they care about doing their job? No, what do they care about? Eat, grow, eat, grow, eat, grow, eat, grow. That's all it cares about, right? It is just constantly eating and growing, eating, growing, eating, growing. That's why tumors will grow really, really, really rapidly, right? Okay, so a key point of cancer is rapid cell growth. Okay, so if you give two kinds of cells, let's say you have two petri dishes, one petri dish has cancer cells and one has normal cells. If you irradiate both of them, which ones are going to accumulate more radiation? Why? The cancer cells, but why? Because of that rapid division rate. Because the more they replicate, the more external environmental stuff they take in. So same thing's true about chemotherapy, right? Chemotherapy is giving a toxin to people's bodies, right? You put it in an IV and you hook them up. And what does it do? It makes them really sick, right? Why does it make them really sick? Why do they throw up? No, actually. So chemo works on all cells. And we know that cancer cells pick up more chemo or radiation, whatever it is, than healthy cells because they are replicating rapidly. Where are the most rapidly replicating normal cells in your body? Your stomach, the lining of your stomach, because you produce hydrochloric acid every second. So your body has to remake the lining of your stomach all the time. So all cells that are rapidly dividing will be most affected by chemotherapy and radiation. So you're going to be sick. What else is going to happen to you? You're going to lose your hair. Why are you going to lose your hair? That's another site of rapidly growing cells. So the side effects of chemotherapy are that healthy, rapidly replicating cells are going to become sick and die because they're taking up as much of the radiation and the chemotherapy as a cancer cell. But the point is that those cancer cells will die, right? We want to give enough chemo and enough radiation to kill those cancer cells. If you don't give them enough, what happens? You might shrink the mass, but as soon as you stop giving them chemo and radiation, what happens? Comes back, right? That's the methodology behind chemotherapy and radiation, right? So how do we want to say this? So this is, we'll say radiation and chemo, right? So rapid cell growth means that they're taking in all of the external environmental substances. At a faster rate. Faster rate. So what do? They die, but if you took enough chemo and radiation, you would die. So it's not just that they die, but they're going to die first. And that's the rationale. So we're really hoping that the treatment kills the cancer before it kills you. But there can be a lot of really bad side effects of chemo and radiation. And that's why, because it's non-specific, it kills everything. So the more we can target it to exactly where the cancer is, the better off the patients can be. I kind of got off on a sidetrack there, huh? That's okay, right? It was interesting. Okay. So I don't think we did. Did we do this? We didn't do this one. Okay. How many simultaneous chest x-rays would a person have to endure to have an exposure of 20,000 millirems? 20,000 millirems is our first kind of indication that you're getting too much exposure, right? You're actually starting to accumulate damage. And the reason that we know this is because people who have accumulated this much exposure will actually see a decrease in their white blood cell count. So we know that white blood cells replicate relatively quickly compared to other cell types. And so we can actually see that being harmful. So based on this example, then is one chest x-ray harmful? So let's find out how many chest x-rays would we have to have? Did I do this one? I didn't do 27. Which one didn't I do? This is so, yeah, okay, so I did this one, right? We said 20,000 millirems. I must have just, bad about that, okay? So we said 20,000 millirems, and I want to know for one x-ray is 5 millirems. So all I have to do is do 20,000 divided by 5. So I get 4,000 sets of x-rays before it gets harmful to my body. So is one chest x-ray harmful? No, it's okay. But who needs to worry about that? Who might be exposed to 4,000 sets of x-rays? The x-ray techs. So what do x-ray techs do? They wear those big aprons. Sometimes they go in the other room, right? And it's important to monitor that. They also wear a badge. And this badge monitors your lifetime amount of radiation. So when I worked at Tulane in New Orleans for a while at the Cancer Research Consortium. And I had a badge because I worked with radiation, and that badge is linked to your social security number. So if I change labs, if I go work as an x-ray technician, whatever it is, it's an accumulation number, right? So your badge is associated with you, and it monitors how much exposure you've gotten. And if you get a new one, right, they take the old one, they measure how much was exposed, and then they add it, and they add it.
So it kind of just like pauses and then you start again.
Yeah, it just pauses. I would have to call safety, and I get a new badge out, and then that would add on to what my history already was. Well, it's really important, right? It's really important. And you don't want to not know you're being exposed, and you are being exposed. Okay. So, okay, let's do this one. Routine dental exam includes 4 bite wings, exposing 5 millirems. Would this cause radiation sickness to the patient? No, it wouldn't. You're fine. It's good. What would be the effects? None. You're fine. Okay. You're fine. All right, let's see. Okay, so we did this. I always forget what I've done on the video and what I have not. I really did all this on the video? All right. Okay. Oh, I think I put myself a note on this one. I did. Okay. On the video, I did section 2.5, numbers 2.29, A, B, and C, and then I did D from 2.30. So I don't know how I did that, but I did that.
I was like, I can't tell her that it's not right.
It's like, you want to tell me, but I'm on a recording. So I realized that I did it. So we're going to go back and we'll pick up D. We'll go back and pick it up. Okay. So now in chemistry, we like to keep track of what happens to all these particles and what we would need to do to make some of these particles radioactive and all that kind of stuff. And so that's why we look at nuclear equations. So what do you think we're going to be worried about with nuclear equations? What's in the nucleus? Protons and neutrons, right? So that's really what we need to be very careful about keeping track of, is our protons and our neutrons. And depending on the radiation, sometimes electrons, but not so much. Okay, we have thorium-232. The first thing I do when I read this is I write down my symbol. So what's my symbol for thorium-232? What is thorium? Go look on your best friend. TH, okay, thorium. And where do I put that 232, top or bottom? Remember, the big number goes on top, 232. So what number goes on bottom? 90. That's a little blue number on there, but I don't know what color it is on your periodic table. Is it a particular color? No. Okay. And it undergoes alpha decay. So am I going to add something to this thorium? If I have a particle and I tell you that this particle is going to, I have this particle, let me start again. I have this particle, it's a square. It is going to decay into two triangles. Do I add a triangle? No. I'm telling you that this thing is going to decay into, here's my dotted line, right? Two triangles. Right? Yes? So I started with one thing and it decayed into two. So should I add anything to thorium? No. Okay. So thorium is going to turn into, that's the same thing as decay, alpha. So I need to release an alpha particle. What's an alpha particle? And I don't want the little alpha symbol because that doesn't tell you anything. Helium, 4 and a 2. But that's not the only thing, right? Thorium is not just composed of an alpha particle. There's more to it. So my question is, what's left? Then I can predict my other product. So it's just like a math problem at the top and a math problem at the bottom. So all of these numbers that are going to go here and here must add up to 232. Then all these numbers must add up to 90. Does that make sense? Just like a math problem. Okay, so tell me the numbers first. What should go on the red line? 228. How did you get that? 232 minus 4 is 228. So 228 plus 4 is 232. Okay, now how about the blue line? 90 minus 2 is 88, because if I take 88 plus 2, I get 90. Y'all see how we did that? Okay, now which of these numbers do I use to go look on the periodic table to find my symbol? The bottom, the smaller number. So look on the periodic table, find 88. What is 88? Radium. So we're really balancing an equation, but we're not balancing coefficients. What are we balancing? Protons and neutrons, right? Okay, let's do B. Strontium 92. What is my symbol? Strontium, and does 92 go top or bottom? Top, and look on strontium. What's my atomic number? 38. And it is undergoing beta decay. So do I add anything to strontium? No, because it's decaying. It's breaking down. It's beta decay. So I could put a beta, but that wouldn't help anybody. So what's the symbol for beta? It's an E with a 0 and a -1. because we've lost a proton and that turns into an electron and a neutron, so our mass doesn't change. Okay, all right, so now my blue numbers have to equal on either side of the equation, and then my red numbers have to equal on either side of the equation. So what goes on the red line? 92, that hadn't changed. How about on the blue? What do I have? So do the math, do algebraically, 38 is equal to -1 plus x. What happens to that -1? +1, 38, 39 is equal to x, right? Because that cancels. Yeah? Okay. So always just set it up just like a math problem. So what do we get? 39. Now go look and find 39. What's 39? Y, yttrium. So just do that where you're making the protons and the neutrons equal. Okay, so now we're not going to do D, we're going to do this D. We're going to do carbon 11 undergoing positron emission. No. Oh, we got to do C. We got to do C. I'm getting ahead of myself, yeah. Okay. Nitrogen 13. Where does the 13 go? At the top. What goes at the bottom? 7. Okay. And it's going to undergo positron emission. Emission is kind of the same thing as decay. Emission, something is emitting, something is leaving, right? You're not adding something, you're removing something. Okay, so it goes on the other side of the arrow. So what is a positron? Remember we said positron and beta were really similar. What was different? The beta is a negative, the positron's positive one, right? But we just don't write it, we just put a 1. Okay, so now we just need to make our reds equal and we need to make our blues equal. So what should go on the red line? 13. What should go on the blue line? 6. What's my symbol? It's carbon. Yeah? Okay. So now we got to go pick up this D right here. All right. So we're going to go carbon 11. Where does the 11 go? Top or bottom? Top. Okay. Yields, it undergoes positron emission. We just did a positron emission, right? So that is E, 0 and 1. Let me move up a little bit. Okay. So now we need to make our reds. Oh, what's our carbon? I'm sorry, look, I didn't fill it out. What goes at the bottom of carbon? Okay. And then we got to make our blues equal out. So tell me what goes in the red line? 11. What goes on the blue line? 5. What symbol? Boron. Boron. Okay, pretty good. All right, so now we just have one left, right? Write a balanced nuclear equation for the production of iodine-131 used in the treatment of some cancers from the beta decay of Tellurium-131. Ooh, okay. So where does iodine-131 go? On the left or the right? Is it a reactant or a product? This is a product. How did you know that? Production. So this is a product. It's a good key. Product, production. Used in the treatment of some cancers from the beta decay of Tellurium-131. So is Tellurium-131 product or reactant? It's a reactant. And the beta decay, what is beta decay? Is that reactant or product?
Oh, wait. No, it's on the.
It's a product. You got to think about it. You got to really think about it because what it's saying is Tellurium. What's the symbol for Tellurium? Go look it up. It's an easy one. TE. So TE 131, and what symbol goes at the bottom? What? 52. Okay, so we're saying that we have the beta decay of tellurium. So tellurium is decaying, and as it decays, it releases a beta particle and iodine 131. So really, they've given you the whole equation. All it is putting it in the right place for this one. So what's the symbol for a beta particle? Remember, beta and positron are the ones that look really similar. So it's an E, 0 and a 1, plus, what is my other product? Beta, yes, negative. Sorry. What's iodine 131 symbol? I, and where's the 131 go? At the top, and what goes at the bottom? So iodine should be 53. Did we have to do the math on anything? Not for that one. Does it work though? 53 minus 1 is 52. 131 plus 0 is 131. Yeah, not too bad, right? I can do this. They'll got this. They'll got this. All right, let's see. I think we'll stop there because we only have one more day, and then, yeah. And we'll talk about radiation units and half-lives next time. If you have any questions, let me know. But you need to start studying. You should be able to do most of the homework. Okay. Anybody need anything? Do not forget, if you have accommodations through the Student Access Center or the Dyslexia Center, you need to make an exam request. Okay. All right. Thank y'all. Y'all have a great day. Anybody on chat need anything? I'm going to go ahead and end Zoom if you do not. Okay. Oops.